So the thing about the second semester is, basically this is going to be reactions. This is how I can summarize this course. So if that was not a strong suit for you last time, then you kind of got your work cut out for you. Okay, because this is really the key. We're going to go through it, divide it into the functional groups, but what we're really trying to get at is how can we do these transformations, right? These organic reactions with each of the groups. So, if you go on a Blackboard also, all of the reaction sheets are up there. And that includes the reaction sheets from last semester. Okay, because it's all together, right? We're going to need all of that information in order to be able to do the conversions that second semester is going to go over. We're going to go over the second semester. So it's a lot of reactions. It's hundreds of reactions. Okay, so usually that's one of the main challenges of organic chemistry is memorizing all of these reactions, right? But I don't like memorizing things. Now I have a photographic memory, so I guess that helps. But I already told the students from last semester that it took me 3 times to learn organic chemistry. Okay, so it's been a challenge. It's not just, memorizing all of this doesn't solve all the problems either, is what I'm trying to say. So, the way I like to approach this semester is to try to include logic, right? So what's logic? Okay, it's finding patterns, right? So how can we take these hundreds of reactions that we have to know and figure out a pattern to learn them, right? Like learn, not memorize. Does that make sense? So I have a 4-year-old, and there is actually a logics book for preschoolers. So I actually bought it for him. Actually, I think I bought it for myself because I'm learning a lot of tricks to to logic. But not really. Like, I feel like I'm a logical person, but teaching logic is difficult, and when you there's different ways of thinking about this, right? But
it's like teaching common sense.
Correct. Which my husband says I don't have a lot of that, so logic and common sense might not go hand in hand here, but that's a way I would like you to think about this course. Now, if you have a photographic memory or maybe memorizing things comes easy for you, by all means. I'm not saying you cannot approach the course that way, but I want to give you an alternative, and I think something that has been useful for me, okay, as I have to teach these hundreds of reactions too, right? So really what it comes down is the pattern. So the pattern to me is how many reaction types are there, right? Okay, so that's what I gave you because I don't believe it's not in your lecture books. It's something I included last semester or last spring, and I didn't update the books yet. So I wanted you to have that handout. But really there's 5 different types of reactions, and we've covered all of them in first semester. So you already know all the stuff. It's not going to be brand new, but it's going to look new. That's the problem with finding, right? The pattern has to be there, but it's finding out, okay, which of these reactions fits the pattern. So acid-base, which we're really not going to see it called acid-base this semester. We're going to see it as proton transfer. So either you protonate, which means you add the hydrogen, or you deprotonate, which means you're removing the hydrogen. But acid-base is really the type of reaction, and we learned that back in chapter 4 last semester, and you learned that in general chem, right? Spent a lot of time doing acids and bases in general chemistry. Okay, so this should be very familiar to you. So that's really the first type. Okay, the next type is redox. Okay, so these are reduction-oxidation reactions, which has to do in organic chemistry with a gain or loss of oxygen. So if you gain oxygen, that's oxidation. If you lose oxygen, that's reduction. Does that make sense? But keep in mind that that also, right, means when you gain the hydrogen, in order to do that, you have to lose, or I'm sorry, the oxygen, you have to lose the hydrogen. So there is also, another way of thinking about this. A reduction would be a gain of hydrogen, which is usually how it's presented by the book. So, I think in terms of oxygen, but there is a loss and gain of hydrogens too. Okay, so we want to keep that in mind. But redox, we also spent a good bit of time with this in general chem. Remember those half reactions, and you had to calculate the electrons, and right. So that shouldn't be new. Okay, but again, finding how can we use this as a pattern. Then the addition reaction. So when you add, right, new bond, okay, new bonds, new atoms to the carbons, right? And usually this has to do with a double bond or a triple bond. So you're going to take that pi bond, break it, and then you have the ability to add two new things. So these are known as addition reactions, adding new atoms. You also can substitute atoms, right? So substitution reactions, so if something leaves, right, that leaving group leaves, and then a new atom comes in. Usually the nucleophile is how we've seen it, but there's actually other types of substitutions. Okay, so there's an exchange of atoms. Does that make sense? Something has to go. So that's 4, and then 5 is elimination. We can also lose atoms, right? Get rid of them. Okay, here we're actually adding, right, new ones, these two. Okay, we can also lose them to get what? The pi bond back. Does that make sense? So really, like these 3, right, here go hand in hand. So often they compete with each other and things like that. Definitely, we spend time on substitution eliminations at the very end of the semester, right? So hopefully that's kind of fresh still. But does this make sense? So really, all of the reactions that we're going to cover should fit one of these patterns. Now, there's a few new ones, okay? And I'll highlight those specifically when we get to them. And of course, if you really love organic chemistry, or you go to graduate school and decide to focus on organic chemistry, you'll take advanced organic chemistry. They'll give you more reactions than this, okay? But I'm talking about how can we get through a general organic chemistry course, right? Okay, so these 5 should get you through if you can learn the pattern. Does this make sense, what I'm trying to do here then? So yes, there will be lots of reactions. I meant to print out all the reaction sheets so you can see how many there are, but you can, I ran out of time. Diego was talking to me too long today. I'm going to blame everything on Diego today.
Sounds like a good pattern.
But you can see there are a lot. But I hope that we can focus on this, these 5 and use them as a pattern for us. So starting with alcohols, how many of these reactions do you think alcohol can undergo? So what's an alcohol? It's an OH group, right?
You go through redox.
So yeah, definitely redox, right? You can oxidize, we can reduce, right? Oxygens for sure. What else do you think?
All 5.
Not all 5 actually, but close. Definitely acid and base as well, right? Protonating, we saw that before where we have to protonate the oxygen of the alcohol in order to have a leaving group that is water. So that's a protonation reaction. And then sometimes we have to deprotonate to form the alcohol when we have the oxonium ion as part of our reaction mechanism. Okay. We definitely saw substitution, right, where the OH left. That was the leaving group. And it was also the nucleophile. Remember, the hydroxide ion was a great nucleophile. So it definitely undergoes that, which means it also has a path to elimination under the correct conditions. Okay, so the only reaction it does not undergo is addition. Okay, now let's say the alcohol has a double bond somewhere in its structure. Now then it could undergo elimination, addition as well. Does that make sense? But just the functional group alcohol can undergo 4 out of the 5. Does that make sense? Remember, for addition, you must have that pi bond to break, and then you add the new atoms, right? So alcohols, okay, the OH group is not a double bond, so we don't see addition reactions. Does this make sense when you think about it? Right, logically think about it. And again, this is just a start, and we'll keep focusing, but I wanted you to have that slide there with the 5 reactions, so using logic. But chapter 10, alcohols, is where we'll begin the second semester. So what is an alcohol? Okay, it is a sp3 hybridized carbon, which means a carbon with 4 groups attached. Okay, one of those groups is a hydroxyl. So not to be confused with the hydroxide. It looks a lot like the hydroxide, but it is not basic. So that's where you want to make the distinction. Okay, that OH, okay, it's called the hydroxyl, YL. Okay, not the hydroxide. And the angles, remember that it's 109.5 is how we have as the angles for an sp3 hybridized carbon, but it's a little bit different, so 108.9, pretty close, but it has to do with the lone pairs around the oxygen. Remember that there's a bend that happens there, so there's a little bit of an angle change because of those lone pairs, but it's pretty close. Okay, so if you drew it right correctly, here's flat, right, 2D, but if you were doing the geometry, it would look like that. So you can see the 109 is due to the bend that happens with the lone pairs. The lone pairs will be up here, pushing down on the hydrogen. Okay, and then you can see that the carbons are closer to that 109.5 because there's no lone pairs associated. Does that make sense? So an alcohol is basically a carbon with the hydroxyl group attached. And of course, this carbon chain can be of many lengths. It can be cyclic, it can be linear, it can be branched, you name it. Lots of different ways. Okay? So after looking at the structure, we do the naming. And again, we already went over all of this beginning of last semester, but I know that seems like a lifetime ago. So we'll refresh every time that we cover a new functional group. So, but remember that the first thing you do when you use the Iupac rules is look for the longest continuous chain. And in the case of the alcohol, it has to contain the carbon with the OH group. All right, so that's the longest chain that has that carbon included. Then you want to number the carbon that has the OH with the lowest possible locator. Okay, so that's the priority. So if there's something else like a double bond or a triple bond, that's second to giving that carbon with the hydroxyl group the lowest number. And then how do I know it's an alcohol? You drop the E from the suffix and then you add all for alcohol. Right? So remember this was pentane, right? This is the number of carbons, right? The prefix, right? Then AN is the infix, which is it double bonds, single bonds, triple bonds? And then the E in this case is going to be the suffix, and that's what tells you what functional group is present. In pentane, there is no functional group, so that's why the E is still there, right? Pentane is just 5 carbons, if you forgot, right? So you may want to refresh your prefixes there. So what we're doing is dropping the E, right, and making this pentanol, right? So now we know there's an alcohol, but we have to say where is that alcohol group, right? It could be in the first carbon, which is 1 pentanol. It could be in the second carbon, which is 2 pentanol. It could even be in the third carbon, which is 3 pentanol. Does that make sense? So you have to locate. So 1, right, pentanol, it would be at the beginning, or you can do it at the end, right? Does that make sense? Just briefly here, I know we've already done this. Of course, there's common names associated, so this is the Iupac part, but you can also name it alcohol with the alkyl group as your substituent name. So this would be 5, which is pentol, right? And then you would call it alcohol, pentol alcohol. Does that make sense? So the carbon chain becomes that substituent name. Is that coming back to you? All right, so these are examples then here. Okay, so you have 3 carbons with the alcohol on that first one, so 1 propanol. Again, it's 3 carbons, so you could call it propyl and then add the alcohol afterwards, and that's what a common name would be for this alcohol. And then isopropyl is at the 2 position, so still 3 carbons, but remember the iso means it's branched, right? Those branches. Remember iso, sec, excuse me. So this is the sec butyl, again second carbon, so secondary there. Okay, it's also 2 butanol, 4 carbons. Okay, and then here there's a carbon substituent, so it's 2 methyl, and then the 1 is where the alcohol is. You give it the lowest number, so 2 methyl 1 propanol, isobutyl alcohol. And then here you have the tert butyl with the 3, okay, for the common name. But again, it's 2, right? The methyl is off of the second carbon there. So 2-methyl-2-propanol. And you can also have a cyclic structure, right? So this is cyclohexanol with the OH attached, and then you have a methyl at carbon number 3. And then don't forget what the wedges mean, right? If they're both wedges, they're cis. If one is wedge and one is dash, it would have been trans, right? Remember that? Again, from last semester. Is that coming back? All right, so that's with one, right? One hydroxyl group, but you may have multiple hydroxyl groups. So diols, triols, tetrols, pentols, you name it. Okay, you can have a number of alcohols there. But we'll focus on 2 or 3. Again, okay, this course is still a basic general organic chemistry course. So with 2 carbons and 2 hydroxyls, right? So that's 1,2-ethane diol. This is also known as ethylene glycol, which is what's on the de-icers. You may have used a lot of this over the weekend since it got really cold. Okay, so that's found in the de-icer component. This is propane, 3 carbons, and you have 1 and 2 again. So 1,2-propane diol, that's propylene glycol. And this is actually in medicines like NyQuil. So you can drink this one. Can you drink this one? Yeah, no way. Okay, that's a poison. People have died from drinking de-icers. So poisonous. And then again, diol here, propane, now 1, 2, 3. And then this one is a triol, propane still, positions 1, 2, and 3, right? So 1, 2, 3 propane triol. And this is glycerol or glycerin, which you might also have heard in your biology courses, because this is a substance that we have naturally in our bodies. So it happens to be an alcohol. Does that make sense? So, and you're welcome to use the common names if you like to remember those, that's fine. But Iupac should always be able to give you the name as well. So alcohols there. And then unsaturated. So like I mentioned, sometimes you may have a double or triple bond somewhere, okay, in your molecule. It's not going to be where the alcohol is, because that's called an enol. And remember, enols tautomerize to the ketose. So enols actually don't exist. So you wouldn't be able to have a double bond right with the carbon that has the hydroxyl group, because it would convert itself to the ketone, double bond between C and O. Okay? But you may have a double bond somewhere else in your molecule. So in this case, okay, you see that the double bond is over here. So remember that the carbon with the hydroxyl gets the priority. So it's 1, 2, 3, right? You're going to count this way rather than 1, 2, 3. Does that make sense? Okay, so this is going to be propene, 2 propene, right? But it's 1 where the alcohol is. Does that make sense? Okay. So 2, right, is where the propene, the double bond is, between 2 and 3. But it's 1, right, where the alcohol is. So 2 propene, 1 all. So what do we think for B? Carbons to start there. 6. So hex. So 2 hex, right? Hexene, 1 all. That makes sense? So it's still at carbon 2, right? 1, 2. Okay, but it's 6 carbons long instead of 3 carbons long. Okay. So you may have a double or a triple bond as part of your molecule, and that's what I mean. This particular alcohol could undergo an addition, correct? Where would the addition reaction happen though? Where the double bond is. Nothing would happen with the alcohol. Does that make sense? So alcohol, the functional group alcohol, will not undergo the addition. But there may be a double bond in that structure that could undergo the addition. Does that make sense? So that's something to consider. So that's naming. Are you all right? Again, the nomenclature, the PowerPoints, that's back up on the Blackboard site for you to look it up. And now again, we'll review every time we have new naming. So now for physical properties. So alcohols are polar. So remember, a polar molecule is a molecule that has part positive, part negative, which we call that a dipole, right? So because oxygen is electronegative, it's actually one of the most electronegative atoms, right, on the periodic table. It is going to pull the electrons towards it, both from the hydrogen and from the carbon, which are both less electronegative than the oxygen. So you see that you get that negative, right, charge right on top of the oxygen, and you can see that here with the red, right? That means electrons, negative charge, and then the blue is a positive or a lack of electrons. That makes sense? And then green is neutral. Okay, so there's a dipole over the oxygen, between the oxygen and the other atoms is attached to. Okay, so just the definition again down here is something we've covered before. The dipole, positive end, and a negative end. So that makes a big difference as to how alcohols interact. Okay, because they're polar, okay, they can undergo a few things. One of them is hydrogen bonding. So not only is it polar, but it's polar containing N, O, or F. That's how you get hydrogen bonding. You have a hydrogen attached to the oxygen. Okay, and a hydrogen bond, it is a pretty strong bond, but it is not as strong as, say, a covalent bond or even an ionic bond. It's still just an interaction, okay? But it is pretty strong, and it can do some pretty amazing things. I don't know if anybody's ever seen this or in class or online or whatnot, but there's actually, right, insects that can walk on water. Have you seen this before? Or, you know, maybe even in physics you might have mentioned this. Okay, but that has to do with hydrogen bonding in water. So water molecules also undergo hydrogen bonding because they have an oxygen with a hydrogen attached. And so what happens is those interactions, they almost form a solid surface. Okay, and that's called surface tension, okay, of water. And so if you apply just the correct pressure and it's just the right the thickness of the material that's touching the water, you can actually stay on the surface, and that's what happens with this particular insect. You can also do this with a paper clip if you're very patient, okay, and you're very careful not to disrupt the water with your fingers. You can actually make a paper clip, okay, float on the water because of the surface tension. So ask Dr. Johnson to do that in lab. And I got a video here, which is of the insect walking on water. So if you want to check it out, you can do that as well. So, we have to move on. This is just for your own curiosity. Plus, you can also Google it. Google it. But hydrogen bonding is between, right, alcohol molecules. So let's say you had two ethanol molecules. So ethanol is two carbons with a hydroxyl group. Okay, they're again going to form this interaction. Okay, so similar to what happens. But do you think that surface tension would work with alcohol? Do you think if I tried the paper clip experiment with water, okay, versus with ethanol, do you think it would work? No. Okay, the strength and the length, that really it becomes about the length with water because it's an O and then the H on the other side. There's a lot more water molecules that can pack together to hold that surface. With the alcohol, the longer that carbon chain, the further away the molecules have to be from each other, that you do not establish a full surface. Does that make sense? So that's really only for water. So even though hydrogen bonding is occurring here, you're not going to have surface tension with alcohols. And you know, methanol is a gas, so we couldn't do it with methanol anyways. It has to be a liquid surface. But that's just one property. Another property that we want to talk about is isomers. So this ability to have the same molecular formula but different structures. Okay, so that's known as structural or constitutional isomers. And alcohols can form constitutional isomers with ethers, which is actually in the next chapter, chapter 11. Okay, and so the alcohol has the OH the hydroxyl group here, so you can see that the boiling point is actually pretty high because hydrogen bonding does increase the boiling point. Okay, the ether, notice there's an oxygen, 2 carbons, right, and that hydrogen is still there. Instead of 2, it's a 3, right, so it does add up to 6, if that makes sense, but the H is not attached to the oxygen, so there is no hydrogen bonding in ethers. So you notice that there's a huge difference in the boiling points, right, so a much, much lower boiling point for ether. Does that make sense? So being able to form, right, these isomers is important, okay, because it does form different physical properties. So alcohols are going to have much higher boiling points, melting points, okay, than ethers, which have the same molecular formula but no hydrogen bonding. Okay, so that's what's on here. No hydrogen attached to that O. But in relationship to alkanes, so remember the alkanes are only carbons and hydrogens. There is no functional group. There's no oxygen. You're going to have a big change in the boiling points, right? Alcohols are going to have much higher boiling points, but also in solubility. So remember that like dissolves like. So water is polar, ethanol is polar, right? Alcohols are polar. They're going to be able to dissolve in water for the most part, up to 5 carbons. That's usually the rule. Okay? But alkanes, because they do not have any, right, hydrogen, oxygen or nitrogen or any electronegative atom, any dipole forming, they're completely insoluble. They're considered non-polar. So can they dissolve in nothing? No, they'll dissolve in non-polar, right? So there's organic solvents that we would be able to use to dissolve the alkanes. Okay, but they would not dissolve in water, insoluble. Okay, but you add 1 alcohol, okay, now the solubility starts to go down. Okay, if you add additional hydroxyl groups, the solubility increases. So the more hydroxyl groups, the better the solubility. Because the solubility doesn't have to do only with the dipole, it also has to do with the hydrogen bonding. So with 2 hydroxyl groups, you can do additional hydrogen bonds with water. So there's 2 things happening here. But the solubility is improved. So those are usually the 2 physical properties we talk about, right? Boiling point, okay, and then sometimes melting point if they're solids, but boiling point and solubility in water. And then again, don't memorize this table, it's just to give you a comparison, okay, and again, it's going to be similar molecular weights, okay, and then it's going to be 1 alcohol, right, and 1 hydrocarbon here, alkane, and you can see the big difference, okay, in the solubility of boiling points. And as they get bigger, okay, you continue to see the same pattern, okay, it changes a bit, but then the other thing you want to consider is isomer as far as branching, okay, and different number of alcohol molecules here. So this is a diol, right, so you would think, right, yeah, bigger boiling point, does that make sense? More soluble. Here I have 1, but I'm 5 carbons, so the solubility starts to drop off here, and you can see the difference between having 1 versus 2 alcohols. So again, don't, not to memorize these numbers, but just to give you a comparison here, a trend. Use your logic here as well, right? Find the pattern. For a 4-year-old, it's like different shapes, and numbers and sequence. So it seems really easy, but it's some nice techniques there. Hopefully my son will be a genius. Just kidding. I already think he is a genius. That's just me. Well, moms always think their children are geniuses. All right. So now for chemical properties. So those are physical properties. But chemical properties, we'll start with acidity. So as I mentioned, even though the hydroxyl looks like a hydroxide ion, alcohols are not basic. They're not acidic either. They're actually considered neutral. Okay, if you recall the pKa, right, it's right about the same as water, which is 16, right? So these are considered to be neutral molecules, neither acidic nor basic. Now, does that mean it will not undergo acid-base reaction? It won't with water, okay? But if you add a strong enough base, you could do acid-base. So that's what you want to consider when you see the combination. So the alcohol itself is not considered acidic or basic, but in the presence of a strong enough base, it will act as acid. Does that make sense? In the presence of a strong enough acid, it will act as base. Does that make sense? And water does the same thing. Okay, but the combination we have here, would this go forward as drawn? No. Right? I can draw these things, but these arrows don't mean the reaction is going to go this way, right? You remember that from last time? Because you can actually have it going right towards like that, right? Or you can do it the opposite. Does that make sense? Where just a little bit, sorry, it's a little bit, but most of it is going back. Does that make sense? So you have to consider what is the combination. The ideal combination is strong acid, strong base, right? That's the best. But sometimes you can take something that's neutral, like an alcohol, and with a strong enough acid or base, you can get it to do the reaction. So that's, remember, a Ka, right, would be 10 to the minus 4 for a strong acid. This is minus 15. So that's a weak, very weak neutral. Okay, and then again, not for you to memorize this, and you know that I give you the pKa tables on the exam, so that should give you a guide there during the test. But you can see again, right, the alcohols, methanol, ethanol, water, right, they're all right there in that middle neutral area. So acetic acid and hydrogen chloride, right, HCl, strong acids, and then you can have more basic. These aren't really considered basic, but it would be something like 35 or higher on the scale. But of course, the smaller the pKa, the stronger the acid. These are the two. And notice the size. As the size increases, so methanol is 1 carbon, ethanol is 2 carbons, right? Propanol is 3. This actually has a 4 carbons total, right? It's propanol, but it has a methyl group also. As you increase the number of carbons, you decrease the pKa. So right? It becomes even worse of an acid, I suppose. So just to keep in mind that the carbon, the size of that carbon chain can affect the acidity and decreases the acidity. Okay. So it does, remember that acidity in general has to do with the stability of the anion that's formed once the hydrogen, right? Remember, an acid is going to donate its hydrogen, so once the hydrogen has left, okay, how stable is that ion? Well, the alkoxide ion is what you would form from an alcohol, and unfortunately, there's nowhere for that charge to go. And so oxygen is considerably small. When you think about sulfur, for instance, is bigger than oxygen, so it can spread the charge. Remember that? Right? Sometimes you'll have a double bond O, right? A conjugated acid, like acetic acid, that helps to move the charge also. But there's nowhere for the charge to go on the oxygen. So that's why the acidity is just about the same as water, which is considered neutral. Okay? But if you add bulk, right, those alkyl groups, okay, the more you have, then the less acidic, because you're going to push actually the electrons back. So that's why you see that decrease in the acidity. So those are actually considered to be electron donating rather than withdrawing. So how could I make that alcohol more acidic? I can add something that is electron withdrawing to the carbon. So I can do the opposite there, but methyl groups are considered to be electron donating. So that's the first thing. The second thing then is, all right, so what kinds of reactions can I do with alcohol? So we'll start with these metal reactions. So lithium, sodium, potassium. So I'm really talking about that first group here. Right? Remember, those are alkaline metals. So not the metals, right, transition metals here, but the alkaline metals. So alcohols can undergo reactions, and notice that what you form is a metal alkoxide. So the sodium is acting as what? So which kind of reaction is this? All right, the hydrogen is leaving, so it's an acid-base reaction. Right? So this isn't really new, but what's the base here? Right, the sodium, right? The hydrogen is leaving, that means that this is the acid, right? By definition, an acid donates the hydrogen, right? And you can see that the hydrogen is here in the form of hydrogen gas, H2. Okay, and then the sodium, right, is becoming the counterpart and stabilizing the negative charge on the oxygen, right? So this is an ionic bond, okay? And because of the formation of that ionic bond, you stabilize the anion enough. So have we seen these kinds of bases? Yeah, in elimination reactions, right? The ethoxide and the methoxide is shown here, but the ethoxide, which is here on the bottom, right, does the same thing. So now you have a conjugate base of your acid, right? And that can act in elimination type reactions if you have a leaving group. But you need to have a base strong enough. That's really the key. So the metal, they will work to form the ions. You can also use sodium hydride. Okay, so that means it already has its own hydrogen as a negative ion. That's really uncommon, but again, with the sodium stabilizing, it works. Okay, that's an extremely strong base. And it's going, again, the hydrogen is going to go, right, to form the hydrogen gas. And then the sodium will go and pair with the alkoxide ion. Does that make sense? So this is, again, we've seen these reactions over and over again. They're just acid-base reactions. It's not brand new. It's just figuring out how is the alcohol fitting in, right? It's fitting in here as the acid. Does that make sense? So these are the metal reactions. Okay. We can also have reactions with the halides, so with HX to form the salt, the halides. So these are better if you have a tertiary alcohol, because what's going to happen is what? What's going to happen with the alcohol? It's going to leave, right? And when it leaves, it's going to form an ion, a carbocation, right? So remember that tertiary carbocations are more stable than secondary. They are more stable than primary. They are more stable than methyl. Remember from last time? So again, it's nothing new, right? These are what kinds of reactions?
Substitution.
Right, substitution reactions. I'm just substituting the leaving group, the hydroxyl, with the Cl, right? So we've done all these reactions before. They're not new, right? Okay, so if you identify, okay, I know this is my leaving group, then my chloride ion must be my nucleophile, right? It's going to attack. Does that make sense? Do you remember that? I told you, if you learned substitution reactions, right, chapter 9 really well, it would be helpful. And so, what kind of mechanism would this undergo? Sn1 or Sn2? Tertiary alcohols always undergo
Sn2.
Sn1. So remember that the Sn1 is a two-step reaction. It forms the carbocation first, then the nucleophile attacks the carbocation. Okay, so it requires a tertiary, enough stability for the carbocation to exist. Primary, right, in methyl, the carbocation is too unstable, it can't exist. So it has to be a concerted mechanism where the nucleophile and the leaving group, right, that all has to happen at the same time. Does that make sense? So Sn1s would be over here, right? Sn2s would be over here. And then what happens with the secondaries?
It could be any of the four.
Both. Well, we're just talking Sn1, Sn2 right now. But yes, they can undergo elimination as well. But just focusing on this. This is a substitution type reaction, right? From our 5 that we talked about. We want to use our logic, pattern them, right? Does that make sense? So the metal reactions are what? What kind of reaction? What type? Acid base, right? The halide reactions are substitutions. Does that make sense? So they're not gonna, these reactions aren't gonna form really elimination that easily. I mean, I'll show you when they can, but for the most part, this is a substitution. So your choice in substitution is Sn1 or Sn2. Does that make sense? In this case, it would be an Sn1, the one that's shown here. Make sense? Now, what about small one, secondary, primary, right? Okay, under these conditions, because we are saying this is Sn1, is it going to happen? No. Does that make sense? Because we're saying this is Sn1. I'm going to show you the Sn2 counterpart to this. But the way it's drawn, if you had a secondary, small secondary or small primary, it would not happen this way. Okay? They must undergo the concerted down here. So this is primary, would you agree? 1-butanol. This is a primary carbon. Okay, what that means is that the bromide will attack and the OH is going to leave all at the same time. So this is Sn1 over here. Does the solvent make sense?
You mean that's Sn2?
Sn2, sorry, Sn2. Does the solvent make sense? Right, it's a polar protic solvent. Remember that polar protic solvents help Sn2 mechanisms. That makes sense? So again, just thinking about, we learned all this. This is not new. I'm not teaching you a new reaction right now. If you search your notes, we might even have something like that in the notes from last time. I just didn't make it about alcohols, right? Because that wasn't the theme then. That makes sense. So secondary alcohols, though, that's when it's a little tricky because they can actually, depending on size, undergo Sn1, right? And depending on size, they can undergo Sn2. So they are the kind of gray area. You have to think a little bit more about what the conditions are doing, right? The size, whether there's branching, right? That beta blocking, other things can come into play. So the way it's shown, what do you think it's going to be? Sn1 or Sn2?
Sn1. Because the carbocation is formed and it can go onto the.
How do you know a carbocation is formed?
Because there's a bromine. There's two products with
Two
bromine.
products, right? And one is the major product. Does that make sense? So there's two possibilities, right? So this can leave here. Right? Carbocation, and then I could have a shift, right? A hydride shift, and form the second product. Does that make sense? That's a rearrangement product. So since there's rearrangement is only associated with Sn1 mechanisms, right? Sn2 don't form the cation, so there is no rearrangement. You would only get one product. Does that make sense? So that's something else to consider. So in the case that's drawn here, that's would be Sn1. Now what about primary alcohols, right? Okay, so that's going to undergo Sn2 for the most part. However, when there's beta branching, remember that again from last time, then it's going to be hard to attack from the backside. That's the kind of attack that happens. The nucleophile attacks from the opposite end of the nucleophile, the nucleophile attacks from the opposite side as the leaving group because they're both negatively charged. They'll repulse each other. So it's harder to attack here, right? Okay, and so that's why we see this as a product. Right? If this was Sn2, we would say the product, the ER, should be here, where the leaving group leaves. But you don't see that, right? You're going to form a carbocation, and then there's going to be a shift here too. More stable at that place. So actually the bottom one is also Sn1. Does that make sense? Okay, so based on what we just talked about, this is just a summary of what I said here. Right? The reactions are going to undergo, right, the ease of the reaction. The tertiary is going to be the easiest, right? The one that's going to happen the fastest because it's stable for the Sn1 to happen.
What if,
Okay, sorry.
just out of curiosity, what if you add, it was with peroxides, would the BR go at the end?
Yeah, then peroxides would undergo the radical reactions. So remember the BR, the HBr gives you additional products. So here we're not going to involve those because we want to focus on just the substitution outcomes.
Okay.
But yes, if you had the BR, then again you would have the product, right, would be different also. But right now, again, let's just focus on substitution, right, so that we have it in our type. Our type is substitution, right? And right now we're talking about Sn1 substitution. Okay? So remember with Sn1, because you form the carbocations, rearrangements are common. So you have to watch for where's your carbocation going to go. If there's a more stable position next to, then it's going to rearrange. So you want to keep an eye on that. Okay? So for secondary and tertiary, that means this is an Sn1 mechanism with a carbocation intermediate. That's the main reaction that's going to happen. Does that mean Sn2 will not happen? I mean, not for tertiary, right? But for secondary and primary, I could have that, right? So what's the leaving group of an alcohol? The OH. The H.
H positive, the hydroxyl.
The hydroxyl, but as a hydroxide? If it was, it would be a base. So when I do these reactions, I'm not really showing you the whole mechanism. Wouldn't you say that H has to go somewhere first, right? Because this is not a good nucleophile, is it? The Br minus is a good nucleophile, so where that H has to go? I'm not showing you the whole mechanism here, right? So think about that H has to go. Where do you think it's going to go? The only atom that wants, right, electrons is who?
The
Or wants to react here is the O, right? Everything else is pretty happy the way it is. Right? So that H actually goes with the O of the OH to form the leaving group, water. Okay? So keep that in mind that there's a first step in the mechanism that has to happen for alcohols to react. Okay, and this Sn1 is the first type of reaction we're talking about here. So the H has to be picked up here. They changed, they put the hydronium ion, but HCl, HBr, those are acids as well, right, in their own right. But there's an H, right, that has to go. There's a transfer, and this is what kind of reaction? Proton transfer, right? This is acid-base. So Sn1 mechanism is actually two reactions. It's acid-base first to form the oxonium ion, right, which gives you water as a leaving group. So the leaving group of an alcohol is not OH, it's H2O, water. So you have to do this step first every time. Proton transfer. Then, once you have the oxonium ion, the oxygen has too many bonds. So it's going to break the bond between the oxygen and carbon, and that's when you'll form the carbocation of the Sn1 mechanism. Leaving group is water. Okay. And then,
that's when the BR attaches.
yeah, then the BR will attach. That makes sense. Okay, and then you'll form your product.
We're at a stopping.
We are at a stopping point. This is exactly where we're stopping. Okay, but does this make sense? Again, this is nothing new, right? If you took, just touch again on this point that for an alcohol, the leaving group is
The water.
Yes, okay? So when you think about the first step on all of these reactions, you should think of, right, this need to convert the hydroxyl, right, into that oxonium, which leaves as water. Does that make sense? So there's always this first step. Okay, so usually when we talked about Sn1 reactions, we said it was two steps, right? right, making the carbocation for the leaving group leaves, right, and then the attack from the nucleophile. For alcohols, though, this is going to be 3 steps. Does that make sense? Because there's one previous step necessary, right, the one that forms the leaving group. Then the leaving group can leave, form the carbocation, and then the attack from the nucleophile. Does that make sense? So we're adding a step for every reaction, a substitution reaction, that is, for the alcohol. Does that make sense? So I just want to make, a quick point of that. So even though, we learned in chapter 9 that an Sn1 is 2 steps, it is actually 3 when you are dealing with an alcohol. Does that make sense? So how many steps is an Sn2 going to be for an alcohol? 2. Does that make sense? It used to be 1, right, for general substitution when we learned it, but when we are applying that Sn2 concept to alcohols, we have to remember you have to form the leaving group first. So it makes a 1 step now 2 steps. Does that make sense? So if you're asked to draw the mechanism, you have to consider that. Okay, so the leaving group is water, circled there. Does that make sense? Okay, and that step is called a protonation or a proton transfer step. That's going to happen with the alcohol. Does that make sense? So here's the Sn2 mechanism. So we stopped before we started with this slide. So this should be the starting point here, but I wanted to make that point. It is 2 steps, right? Okay, the first step again is protonation. It makes that oxonium ion. The oxonium ion then leaves, right, as water. So I kind of tried to add it in where water is being, right, formed in order to be released as the leaving group. And then you can displace the water with the attack, which is the concerted mechanism that we are used to seeing for an Sn2, right? Nucleophile attacks, leaving group leaves, all at the same time. Does that make sense? So for an alcohol, there's an additional step. That's what I'm trying to get at here. Does that make sense? Okay, but again, remember that it is the, right, concerted that's the determining step, right? The rate determining, the slow step. This proton transfer is rapid and reversible. Does that make sense? So again, in the Sn1, it's the carbocation formation that is the rate determining step. So that hasn't changed, okay? Because that first step is rapid and reversible. So that's not going to be determining the rate. Yeah.
Can you explain the 2 steps again? I'm just a little confused.
Yes, so again, for every alcohol reaction, you have to form the leaving group. So the first step in all of the reactions is forming that oxonium ion, which is through a proton transfer. So you're taking, right, a hydrogen, right, and that has to go with the oxygen to form the oxonium ion, right, which then leaves as water.
Okay. Got it.
So that, I'm basically just, we're adding that first step. So it's a +1 situation, right? We learned Sn1 and Sn2 previously, 2 step, 1 step. But now you have to add that additional step to it. 3 step, 2 step. It's still, yep, the Sn2, that concerted, that's still the rate determining step though. That hasn't changed. So if you think about, that question on the exam where we went, okay, Sn1 is how many steps, right? What's the rate determining step? I'm just trying to give you that for the alcohol. Is it, a little bit different on the number of steps, right? It's 1 more step, but it doesn't change the rate determining step. So that remains the same. So if you think about the things we discussed as important factors in a Sn1, Sn2 mechanism, okay, you just want to adjust them for the alcohol a little bit. So that's the Sn2 here. So this is concerted, as we've seen before. It all happens at the same time. The nucleophile attacks, the leaving group leaves, and then you form the product there. Plus, again, the water is the leaving group. Okay, not the OH alone, right, but the water. Okay, so for primary alcohols, okay, you're going to consider, right, Sn2 as the mechanism. However, if you have the beta branching, right, that becomes an issue. Remember, that's when you have a bulky group attached to your primary carbon, so that makes it hard to attack where you need to, which is from the back side. So Sn2 is not possible, right? Just explained why. The backside attack, that's not going to happen very easily. Sn1 is also not possible, right? Because Sn1 is for tertiaries, right? So primaries don't undergo Sn1. So how can we do these reactions? Or can we, right? The question is, can we? And the answer is yes, you can. But it's really a hybrid. It's a concerted loss of water, which means you do form a carbocation, but you can't leave that carbocation there because that's too unstable. So together with the loss of water, formation of the carbocation, you immediately have to do a alkyl transfer, or when we did the hydride and the alkyl shift for the rearrangement. So basically, it's a hybrid between Sn1 and Sn2. So this is what it would look like here. So again, right, there's a bulky group here. That's the beta branching that we're referring to. So the attack should happen here, right? But it can't. There's something in the way, right? So what can I do? Okay, again, a hybrid between the two. Of course, first step always, right? Protonation form the oxonium. So that's proton transfer happening there. So the concerted elimination is down here. So you have to get rid of water, right? But you can't leave the carbocation here. Does that make sense? Because that's too unstable. So at the same time that water leaves, the shift has to happen so that the carbocation is actually here, where it's stable. Does that make sense? Right? If the leaving group leaves here and nothing happens with the shift, that's too unstable to be a carbocation, right? So you have to have a concerted mechanism also, but the concerted here is not the nucleophile attacking, but the alkyl shift has to happen. Does that make sense? It's still concerted, but it's a little bit different, right? Not a nucleophile here. Does this make sense? So you're converting the primary to a tertiary carbocation. You have to. Does that make sense?
So that one is, it can't be on that, that can't be a carbocation. Why is it too unstable?
So this is primary, right? So if this leaves, then we would have, right, if the water left, then the carbocation is here.
Okay.
Without the water, right? That's a primary spot. That's too unstable, right? So remember the tertiary, right? Secondary, primary, right? So Sn1, which forms a carbocation, doesn't occur for primary because of this. This is too unstable. So by doing the shift at the same time as the leaving group leaves, you avoid this ever happening. Does that make sense? You just don't have this here, this charge. The charge shows up at the tertiary. Does that make sense? So you kind of bypassing having that unstable primary carbocation. Does that make sense? And it can happen because you have the bulky, right? The 3 methyl groups here available for the shift. So that's the concerted part. Does that make sense? So that's for the beta branching there. And then now I do have a carbocation, so where's the attack going to be, right? Over here, where the carbocation is. Does that make sense? So the product is now going to have, right, your nucleophile here. The nucleophile is going to be rearranged. So it's kind of a hybrid. It's in between. There's a concerted element to it, but the concerted element is the shift, the methyl shift, while the leaving group leaves. Okay? So if you're dealing with a primary, what mechanism is it? Just primary. Sn2, right? A primary with the beta branching, this hybrid thing, right? Okay, it's not really an Sn1, it's not really an Sn2, it's a hybrid, a different mechanism. right? And if you had tertiary, you would have Sn1, right? And of course, the secondary gives us, right, multiple choices. Does that make sense? So that's, in a nutshell, trying to summarize the reaction with the HX here. Okay. So you just want to keep that in mind as you're asked to draw products. Okay, consider that if you have the beta branching, you're going to have that rearrangement. Does that make sense? All right, so that's the HX, but that's not the only way that you can add, for instance, a bromide. Okay, there's a alternative mechanism which uses PBr3, so phosphorus tribromide. Okay, this works for primary and secondary. Okay, so you can see that there is an alternative, and this alternative, and I told you that last semester, usually when we show you an alternative is because there's something that is advantageous of using another reagent. And so the advantage here is that you do not have as much rearrangement. So the mechanism we just talked about, right, it's going to lead to a rearrangement every time. This has to happen, right? Okay? With the PBr3, you do not have the rearrangement. Does that make sense? So here we are again, right? We have a branching. So the attack is going to be blocked. Okay, if I was doing a traditional Sn2 mechanism. But this is a different reagent, right? It's not HBr anymore, so it's PBr3. And what that's going to happen is it's going to allow you to do that, okay, that substitution at the primary carbon. Does that make sense? So now you can have the product here. So if you had HBr, the product would be here. If you use PBr3, the product would be here, right? So these are alternative mechanisms, depending on what you want the product to be. Does that make sense? Okay, so is this Sn1 or Sn2? It's still a substitution. Would you agree with me? I'm still substituting the alcohol for, right, the bromide. So the bromine. Okay, is it Sn1 or Sn2? Okay, it is Sn2. Okay, so what happens is that you have a really good leaving group that's formed. And so that's really how you can overcome these issues of the attack. Okay, you put in a extremely efficient leaving group. Okay, and that allows the mechanism to undergo just a straight Sn2 mechanism. Okay, water is considered a poor leaving group, even though it leaves because it's charged on the oxygen. It's not great, okay, because you can remove that hydrogen very easily and return it back to the alcohol. But when you make these kinds of, leaving groups here, okay, so for instance with the PBr2 now attached to the oxygen, right, it's still charged, but this isn't going to want to leave, right, by itself. It's going to want to take the whole thing with it. Okay, so that's a really good leaving group. And then, of course, you're coupling with a very good nucleophile, the bromide ion, okay, because it's PBr2, right? The third one is now the nucleophile. Does that make sense? It used to be PBr3. So one of these is leaving. And so this is very efficient as an Sn2, no matter what that R is. So no rearrangement necessary for this mechanism. Does that make sense? If you're keeping, track. Now this is for primary and secondary. It does not work for tertiary. So this only undergoes an Sn2 mechanism this way. Now what about chlorides, right? So in, again, contrast to using HCl, right, which was the HX mechanism we covered previously here, you can use another reagent also, which is known as thionyl chloride, SOCl2, okay? And then again, primary and secondary would be useful here. And this is going to require, though, a base. So you see this over the arrow, that's pyridine, which is a base, an organic base. And it is necessary because the byproduct of this reaction is HCl. HCl is a strong acid, so it needs to be, right, neutralized. Otherwise, it comes back in and it can react with your alcohol. Okay? So we always use a base, and pyridine is usually the one chosen, but triethylamine can also work. Okay? Sn1 or Sn2? Does that make sense? So, you know, it's just I'm going to keep doing this because my goal is that you start to use your logic and categorizing. This is a type of reaction, not just a lone reaction you have to memorize, right? So thionyl chloride does that, right? So another clue that this is Sn1, Sn2 is that it always gives you an inversion of configuration. Remember, that's associated with Sn2. Sn1 gives you a racemic mixture, right, because you have the carbocation, but an Sn2 will give you the inversion of configuration, which means if you start with S, as you see here with the S2 octanol, it gives you a product of R, right? It inverts the configuration from S to R. Okay, and again, that arrow is just showing you here that this is going to be the base. So, does that make sense?
And so that one is,
So this is Sn2, right? So this is another clue. That's why I put it underneath there. So this is giving you another clue that this is going to be Sn2, the inversion part. And this is giving you again that, you know, the reasoning behind this happening as Sn2 is that with the sulfur, with the thionyl chloride, you form another really good leaving group, which is a chlorosulfite. So these sulfur-containing leaving groups, we'll see a few more in just a minute, are really common with alcohol reactions in order to get the reaction to go faster, okay, as a Sn2. And then again, that's right formed from the first step, okay, from the thionyl chloride. One of those chlorides acts as your nucleophile in the second step, okay, attack, leaving group leaves, concerted, right? So that's Sn2. That makes sense. So these sulfonyl chlorides, so they're derivatives of sulfonic acids. And so this is the sulfonic acid here, so the chloride. And then you also can have the sulfonate ion as a good option. Again, transforming the alcohol to a sulfonate forms the good leaving group as well. So there's a number of reactions where that can happen. And sulfonic acid is also a strong acid, like sulfuric acid. So it's from the same family there. And so just a few examples here where you're forming those sulfonates. So you can use paratoluene sulfonyl chloride, so for short TSCl, okay, or you can use the methane sulfonyl chloride. Okay, so thionyl chloride was the one to form the chloride version, but here there's only one Cl, right? So you don't have that attack from the chloride. So what that means is you can actually use what's formed and then attack with whatever nucleophile you want. Does that make sense? When you use thionyl chloride, you have to attack with that extra chloride. So you always form that as a product. When you form these sulfonates using these reagents, then you are free to use whatever nucleophile you want. So again, it opens up a variety of reactions for you to do with your alcohol. Does that make sense? So why am I telling you all this? Because what's the problem? Well, I want you to be smart like me. I'm trying to make you smarter like me. No. But it's because alcohols themselves are not that reactive. That's why we're going over this stuff, is because the OH of the alcohol isn't going to leave just on its own. Right? So what's the first thing you're going to try to do? Protonate, right? Try to make the oxonium ion so it leaves as water. That's all right. That's okay, right? In the presence of a strong acid, that's going to work, okay? But you have other options, right? Converting them to these other good leaving groups with the PDR3, with the thionyl chloride, with these sulfonates. Does that make sense? So that's what the reasoning behind these, 5 or 6 slides. So I don't want you to get lost and, why is she giving us all this? It's because the alcohol itself is not, the OH is not a good enough leaving group on its own. So you can protonate if you have a strong acid, okay? But if not, then you can choose to, do a number of reactions to convert it to a good leaving group. Does that make sense? PBr3, thionyl chloride, and then the sulfonates, right? And the sulfonates, you would convert them using these reagents up here. Does that make sense? And then the good thing about this particular combination here, the sulfonates, is that the nucleophile can be whatever you want. Once you have them in the sulfonate, then you can, do a variety of different reactions. It's not just chloride. Thionyl chloride will only give you the chloride as a product. Does that make sense? Right? The substitution. The PBr3 is only going to give you the bromide. Does that make sense? This you can couple with whatever nucleophile you want. And that's really a key to organic chemistry. I want to be able to do a variety of reactions.
There's so many reactions in the world.
There's so many reactions in the world, right? Lots of things that we want to do, right? So does this help? Kind of, again, so that you're not lost in these last 5 or 6 slides. Like, why does she keep going over this? No, because alcohols themselves aren't going to react all on their own. I don't know why it's doing this. I have to fix it. See how it's turning it to red and turning it to red? And then, I'm not that great with technology, so. No, yeah, don't let her hear that. So this is just a summary of what I just said. So the sulfonates, when you create those sulfonate ions, then you create a very good leaving group, okay, especially for Sn2 reactions. So you can couple with a good nucleophile and you get a fast reaction. So that's really good, okay? And just comparing it to water, right, which is what you get from that protonation step, this is a poor leaving group. I mean, it works, but it's not great. The sulfonic ester, that's going to be better. So you want to consider, again, if you're trying to make the reaction more efficient, faster rate, that you would consider that, which is the previous slide to that. Okay? So those are the substitution reactions. So now we will delve into elimination reactions. So now the questions are going to come like, is it E1 or is it E2, right? Because those are the choices, if you recall from chapter 1. Okay, so alcohols, right, that's a competing reaction. Since they can undergo substitution reactions, they're also going to be able to undergo elimination reaction. And when you do an elimination reaction of an alcohol, you are going to produce water. So these reactions are called dehydration reactions. Okay, D, right, removing, hydro for water. Does that make sense? So you're doing a dehydration of an alcohol, but this is nothing, more than an elimination or beta elimination, which is the type of reaction. Okay, so for primary alcohols, this isn't quite easy. Okay, so this is going to require high temperatures, an acid catalyst, so this is difficult to do, so consider that. For a secondary, it's a little bit better. You can use lower temperatures, but you're still going to need a catalyst, so it's a little bit easier to do. But tertiary alcohols, slightly above room temperature, that's all you need. So hopefully you see that that means tertiary alcohols are favored. So do you think this is E1 or E2? If tertiary is preferred, then it should be E1. Does that make sense? So by reading this description, it should give you that as a mechanism, right? So the more stable the carbocation, the more likely for this reaction to go forward, which means this is leading us to an E1 mechanism. You still need a catalyst, yes. But you don't have to heat it up, which is an indication that it's not as hard to do. But again, the product is going to be, right, you're going to eliminate the OH and then an H from the neighboring carbon, so you get the alkene. Okay, plus, of course, you're getting rid of water, dehydration, right? Same thing, so this is primary, secondary, so same alkene plus water. Okay, and then a tertiary example down here, right, alkene plus water. Okay, but again, notice 180, right, 140, 50, which is barely heating. Does that make sense? So this is, again, thinking of the mechanism, leading us to think U1. Okay, and if that's the case, then we know that we're going to form a carbocation, right? That's part of the E1 mechanism, which then means if you're considering what's that product going to look like, where's the alkene, that double bond, going to go, it's going to have to follow that similar rule to the Markovnikov's rule. For double bonds, we call it the Zaitsev rule, but it's the more stable alkene that's going to be formed. Right, so if we look at the example here, right, the OH is here, so I can technically take a hydrogen from here, the double bond there. Does that make sense? Okay, or I can take the OH here plus the hydrogen on this carbon. Does that make sense? Which would give me this one, right? This is primary, this is secondary, right? So secondary is more stable. So you do get 80% of your product there at the more stable position. Right? You still get some here, okay, but it's not the major product. So again, right, more evidence of E1. Is everybody following? Right, E1 is like Sn1, so it has that carbocation element. See how it's turning red? Push the button, it's blue, and then it goes to red. So it makes it slower than usual. All right, so that's for tertiary. Now, what about primary and secondary alcohols? Can we do this reaction? And the answer is yes, but often you're going to have that rearrangement. Okay, again, you're having the issue of having the carbocation at a unstable or less stable position. So if there is an ability to do the rearrangement, it will happen. Okay, so here, right, you're going to remove the OH here. Okay, you can go this way, or you can go this way, right? So you're going to pick the more stable. Does that make sense? With a shift. So one of these has to go here. So that's why you have that. You might recognize this from an exam from last time. Right, so there was a shift. Would you agree? There's 3 carbons here and 1 here. In the product, there's 2 and 2. Right, so the shift, the rearrangement has happened. I'm always afraid when I say shift that I'm going to say the other S word. On camera. This is going to go on YouTube, isn't it? If I share this with y'all, you might just edit out like the things that I say that are like inappropriate.
And you chose that spot because it's more stable.
Yeah, so you chose it because this is going to be the more stable carbocation, right? Once the shift happens. Tertiary. Yep. Now what about down here, the 1-butanol, right? So again, you're going to assume if this left and this was E2, right, then this would give you this product, right? The double bond would be in the first carbon, right? But you only get that 12% of the time, right? So again, it's leading you to hopefully conclude that there's going to be a hydride shift that's going to happen here. You're not shifting a carbon but a hydrogen, which is also a possibility. So that would give you, right, the other products. And remember that trans is more stable than cis, right? The position of the double bond is the same, but you can either have the trans or the cis, and trans are more stable than cis. So you get a little bit more of that product, so 56%, right, versus the 32. But again, you know, the least favorable product is going to be the E2, right? So this is still proving this is E1. Does that make sense? If you think about the mechanism rather than just memorizing each particular reaction. See how it's turning red, and then
go ahead and hit it
I'm
now.
gonna have to fix it. I don't know how to fix it, so I'm gonna have to research.
I mean, make it red now.
Oh, make it red from, see, I forget, but yeah, that's a good point, I should do that. So based on the evidence, again, just summarizing what I've been saying, so the E's, right, tertiary is easier to do at lower temperatures than secondary than primary, plus the fact that we see rearrangement, that means carbocations are being formed. This is leading us to classify this as E1. Okay? So that's basically the summary there on paper, so you can have it. Okay, now again, this is a 3-step, right? So E1, when we learned it just as a general mechanism, there was 2 steps, right? Form the carbocation, right? Then the double bond, the alkene, okay? Now there's gonna have to be that first step. You're still having to get rid of the oxonium, right, as water. Then the hydrogen is gonna form that double bond. So, and again, eliminated here is water. So it's always the product. So you have that first step as mentioned, right, forming the oxonium ion, okay? And then the oxonium ion leaves, right? You form the carbocation plus the water as the leaving group, okay? E1. And then in step 3, then you remove the hydrogen from the neighbor carbon, okay? And then those electrons go to make your double bond. That makes sense? So it's still, right, that proton transfer step still necessary for the eliminations as well. So E1 becomes 3 steps, E2 becomes 2. Right, E2 is 1 step, right, concerted, but in the situation of alcohols needing to convert the OH, you have that additional step.
Wait, this one's E2?
This is E1. So these that we've been talking so far have been E1 mechanism. So it's 3 steps. The proton transfer, the carbocation, right, leaving group leaves, carbocation is formed, and then you remove the hydrogen to form the pi bond, right, the double bond. So it's 3 steps. Okay, now what about primary alcohols that have little beta branching? Okay, so there is, right, a mechanism for this. So you can form that double bond then at the terminal, right? So again, the protonation, you form the oxonium, right? And that's going to leave as water, but it's going to happen at the same, everything at the same time. So there is an E2 option only for the primary alcohols with little branching. Secondary carbons will undergo E1. Okay? But for primary with, you know, nothing obstructing, so you can't have bulky groups here. Then you can undergo in the E2, again, it's concerted. See, the H leaves, the pi bond forms while the leaving group leaves. Everything is happening at the same time, and that will give you that double bond on the first carbon. Okay, so that is an option, but only for primary alcohols with no beta branch. So, but a little bit of it does shift into rearrangement. So there's a little bit of something that happens here. When you have that oxonium formed, right? So if we go back here for a second, so we're kind of, you know, looking at something like this. For this oxonium, right, formed, there is a possibility of the hydrogen moving over, the hydride shift happening. So then it moves the carbocation into the secondary position, which would give you the E1 product. There's a little bit of that, okay, that goes on too. So for, just keep that in mind. But this isn't supposed to be, right, the major product should be the E2 product. But there is some of that that happens too. And then this is just showing you the rearrangement. It can, right, from the methyl shift, right, to make that tertiary, the one with the 2 carbons on each side, which originally had 3 in 1. This is just showing you that shift. This again, the dehydration is most commonly going to be associated with E1, okay, and that E1 is associated with rearrangement and the more stable alkene product. So we'll see much of, you know, the double bond at the primary carbon product. Does that make sense? The elimination. options, so mostly E1, right, for alcohols, mostly E1. So, and how do you know it's going to be elimination versus substitution again? Remember that from last time? What do you need to do an elimination?
Eliminate.
Base,
Yeah.
right? Remember, you need that organic base, the ethoxide, methoxide, right? Sodium methoxide, right? Or you can have that bulky base, right? The 2-butoxide, remember from last semester? So that's still something you'll want to compare. Is this, going to lead me? Usually, if you notice, all of the substitution had acids, right? So the eliminations, you're still going to run into that. You might want to keep that in your radar is what I meant to say. Okay. Those are eliminations. So the next type of reactions are oxidation reactions. So what's an oxidation reaction? In organic chemistry, this general definition, a gain of oxygen, right? So we're going to be looking at a gain of oxygen for the following set of reactions. So in this case here, you're starting with a glycol. So remember, a glycol by definition is a diol, two hydroxyl groups next to each other on adjacent carbons. So that's a glycol. So this type of reaction, which is called a Pentacle Rearrangement, only occurs with a glycol. So it doesn't occur when you have just one OH group. Okay? You won't have to have two, and they have to be right next to each other, adjacent. So it doesn't happen if the OHs are far apart. They have to be right next to each other. So specific to that. And it gets the name Pentacle because that's what, this is the original reagent for this reaction, and it's called Pentacle. And the product of this is a ketone, right? And that's considered an oxidation, right? Because you're gaining, right, a bond here. Instead of it being a single bond to an oxygen, you're going to a double bond to an oxygen. So it's one type of oxidation, but it's also an elimination, isn't it? You're losing one of these hydroxyls, here, right? And in order to get a double bond here, right, you're going to have to lose something from that carbon as well. So there is an elimination factor here. So this is considered dehydration as well. Okay, so these are the steps then. So of course, hopefully no surprise that there's a proton transfer to one of those hydroxyl groups. You form the oxonium ion. So now you have a leaving group. So the leaving group leaves and it forms your carbocation. Okay, but now is where it gets a little bit different. So the hydrogen, a shift happens here. So you have a methyl shift, and then it forms your carbocation adjacent to the oxygen, right? Or where the oxygen is attached, not adjacent, but directly bonded, carbon that's directly bonded to the oxygen. So now you can actually transfer the electrons, right, one of those lone pairs to form the double bond. So that's how you end up with a ketone. Okay, so there's a shift here, right, the methyl shift to put the charge on the carbon that has, right, the OH that's left attached. And then you can do, right, that pi bond forming from one of the lone pairs of the oxygen. But you're not done, right? This isn't really a ketone. It's still an ion. So the last step is a proton, right, transfer also, but deprotonation. You're removing that hydrogen, and then you get the ketone. Does that make sense? This is the Pentacle rearrangement. So it's an oxidation and also, right, a dehydration, an elimination reaction. And it only happens for the glycol, this particular reagent. So it doesn't happen just for any alcohol. Keep that in mind. So that's a clue there. Okay, so what about the general alcohol? Okay, so let's start with the primary alcohol. Okay, so what's going to be the oxidation in general terms? So what you're going to need is an oxidizing agent, and then you can take the primary alcohol and convert it to an aldehyde or to a carboxylic acid. Okay, so depending, is there a question?
Yeah, what did you say? You said it doesn't happen to all alcohol.
Yeah, so this one only happens for the glycol when there's two, right, diol, and they're next to each other only. So the next set of reactions are the general oxidation. So what happens to most alcohols? Okay, so we're starting with the primary alcohols. What's going to happen to those? Okay, so you can convert them to either an aldehyde, right? So the aldehyde, the double bond O with the H, right? Or you can convert it to the carboxylic acid, right? Double bond O, OH. So that's here. And this is dependent on the experimental conditions. And most often it's going to be the nature and the strength of your oxidizing agent that's going to determine, are you going to make the aldehyde? Are you going to make the carboxylic acid? Okay, so you have to be, aware of that. And of course, the first conversion here, right, to the aldehyde is a 2-electron oxidation. Okay, but you're actually getting an additional, right? If you do another step here, that's an additional oxidation, so it gives you a 4-electron oxidation. So this requires a stronger oxidizing agent. Would you agree? That's going to require that stronger agent. And usually that agent is chromium, okay, or chromic acid. So you can take the chromium 6 oxide, okay, or the potassium dichromate in sulfuric acid, and that makes the chromic as a product. So that's the two ways of getting it. But the chromic acid, the product circled here, that's going to be your oxidizing agent. Okay? And so for the primary alcohol, example here is 1-octanol, it's going to go directly to the carboxylic acid. So the aldehyde that's in the middle here is not isolated. So in theory, we know that there's a step, right, that the aldehyde is there, but it is we are unable to actually isolate that as a product. It kind of goes, this is a very unstable, so quick, right? So all we really get if we use chromic acid with the primary alcohol is the carboxylic acid. Does that make sense? There is an aldehyde in the middle, but we're unable to isolate it. So that's not considered a product of this reaction, okay? Just an intermediate, right? So something that's there but can't be isolated, okay? For a secondary alcohol, if you use chromic acid, right? So now it's secondary, right? 2 carbons attached there, the carbon with the hydroxyl. You get the ketone, okay? Not the aldehyde, but the ketone. Now, can I get the carboxylic acid? Unfortunately not, right? This carbon already has 4 bonds. There are 2 other carbons or oxygen. There's no hydrogen really is the key here, okay? Here, right, 3 bonds, there's a hydrogen you can't see, which needs to be removed. Remember that an oxidation is both a gain of oxygen, but you have to consider a hydrogen is always lost too. So the secondary never goes to the carboxylic acid. It stops at the ketone. Does that make sense? There's no more bonds, right? Nothing else to be lost, no hydrogens to be lost. So this is what chromic acid, okay, and this is what's going to happen. So again, you're forming, right, that good leaving group, and in this case is the chromate ester. So you take the chromic acid, okay, it's going to react with the alcohol, right, to form the leaving group, the chromate, okay, or the ester. And then you can go on to the second step, and the leaving group leaves, right, at the same time as you take the hydrogen, okay, and then you form your double bond. Does that make sense? So then that's how you end up with your ketone in this case. Right? Same thing is going to happen with the primary, okay, but you're going to have an additional step. Turn to red first. So that's chromic acid. So why can't we isolate the aldehyde? Okay, the reason is that when you form that intermediate, it isn't really formed as an aldehyde, but as a hydrate of the aldehyde, right? So the aldehyde should have the double bond O with the H, notice that that's not what you get. You actually get 2 hydroxyl groups, which is called a hydrate. And that's the reason. This is very unstable. It quickly becomes the carboxylic acid. So that is really the reason, even though we know there's an aldehyde intermediate, it doesn't look like the aldehyde. It's a hydrate of the aldehyde. So that's really why it cannot be isolated under the chromic acid conditions. Okay. So that's what ends up happening. And this is just showing you can form, anytime an aldehyde reacts with water, you form the hydrate. So especially small aldehydes, we can't even have it out, exposed to the moisture, the humidity in the air, because it will convert it to the hydrate. So the aldehydes that we have in lab, like acetaldehyde, we have to keep it, without any moisture available. Otherwise, it's no longer the aldehyde. So this happens, and this is happening during the reaction. So what if I want the aldehyde though, right? There is a mechanism for making aldehyde, but you cannot use chromic acid. You have to use PCC, or pyridinium chlorochromate. Okay, so you do form it also from that chromium 6 oxide, but what you're going to react it with is pyridine. So remember, pyridine is a base, and then it forms a complex, which is called the PCC, right? Pyridinium chlorochromate. And if you use PCC, it allows you to stop at the aldehyde. It does not continue to oxidize to the carboxylic acid. Does that make sense? So if you want the aldehyde, you can get it by using a different oxidizing agent. Does that make sense? So when you think oxidation, you should think chromic acid, except when you want an aldehyde. Okay, then you have to switch the reagent. Okay. Now the PCC, you can also use it with secondary alcohols, but you're still going to get the ketone, right? Because remember, the ketone doesn't really get oxidized further to the carboxylic acid. So using PCC or chromic acid is going to give you the same product for a secondary alcohol. The difference is when you use the primary alcohol, right? Chromic acid gives you carboxylic acid, right? The PCC gives you aldehyde. Does that make sense? Reagents? So what about in the body? I just thought this was kind of interesting because, we undergo a number of oxidation reactions in the body, right? Including aging. I know, I feel like that's happening way too fast, right? So oxidation reactions are really important in the body. Now, would I think that chromium or chromic acid is involved in that? Right? Because it is highly toxic. So I don't have, or you don't have, right? We don't have chromium or chromic acid in our bodies. It's a toxic substance. But we know oxidations happen all the time. And so one of the ways that oxidation happens is through NAD+. Have you heard of this? Pretty important, right? Right? Part of respiration. Okay, the Krebs cycle is one of the intermediates that carries those electrons, right? So that we can do oxidative phosphorylation later and make a bunch of ATP. And this is also involved in oxidation. Those are oxidation steps too, okay? The steps that form the intermediates or do the conversions of intermediates. But a number of other enzymes use this NAD+ as an oxidizing agent. And it is this business end is highlighted here, okay? And if you notice, this looks like pyridine. So that PCC reagent has the similar business end. So even though, again, right, we don't have the chromium part, because that's toxic, we have something similar in the body. So I just, again, to put it into some context here, okay, of different reactions in the body. So ethanol, for instance, right, that gets oxidized right, to the acetaldehyde or ethanol, right, and then eventually to acetic acid, which is vinegar, right, and when you take a breathalyzer, has anybody been unfortunate enough to have to do that? I actually haven't, but.
I wasn't drunk.
You weren't drunk, but it happened, yeah. So what they're testing for is acetic acid. Did you know that? Did you watch the Mythbusters where they tried with salt and vinegar chips and like different foods that have vinegar? And then they tried different things to try to cover up, so they got really drunk, and then they tried all these different things that neutralize acetic acid. It was kind of, there was a marathon, did y'all know? Every year, New Year's, my husband watches every single episode again, so I get to have the joy of rewatching. But hey, that one was pretty interesting. But that's what happens, right? It's an oxidation reaction, and alcohol dehydrogenase is the enzyme that does this oxidation, this conversion, and it has the NAD plus as a cofactor, so it uses that as part. And then another one is lactate, right? So lactate plus, again, your intermediate here, lactate dehydrogenase makes pyruvate. Where's this happening? Right? In your muscles, right? That's lactic acid, right? So that's the way that we eventually get rid of the lactic acid that forms. When does lactic acid form? When you work out too hard, right? You overdo, you don't get enough oxygen to the muscles, right? So then the muscles start to go into fermentation and lactic acid forms. But it breaks down over time with the help of this particular enzyme.
And
massages. And massages. Yes. So,
But that's
and
painful.
rest, right? So. But I just thought this was neat because this is, alcohols, right? There's a number of alcohols in our bodies as well, a lot of different reactions, not just when you drink, right? But there's a lot of alcohol circulating there. So a couple other oxidations here that are specific. So glycols can also be oxidized using periodic acid. I always want to say periodic because it looks like the periodic table, but it's periodic, so it's from iodine. So I is iodine here, right? And then it's tetraoxide. So when you have that particular reagent in a glycol, right, again, two diols, so two hydroxyls adjacent to each other, then you can actually break the bond between those two groups. So this bond is actually broken in order to make, right, the two carbonyls. So that's just, a specific reaction, only happens in the presence of this particular reagent, so periodic acid. Okay? And you have to have the glycol, and it forms the two carbonyl groups. So this is the reasoning behind this. Why it happens is that the intermediate is cyclic. So you see, so these are the two carbons that have the diol there, the glycol formation. And then this here, right, is that cyclic intermediate that forms with the iodine from the periodic acid. And when it's cyclic like this, you can do a redistribution of the electrons since they're all connected. And so when you do that, you can actually break this bond. So see, this shift here makes a double bond, right? And this makes the other double bond. So there's nothing left in between the two. Does that make sense? So this, right, is going here to form the double bond, and this one is going here to form the double bond. So there's never a shift back. Does that make sense? So it breaks that bond to form the two carbonyls. Okay, so again, it's an oxidation, right? You gain that bond to the oxygen, but it's a, a different reagent that forms a totally different product as well for the glycols. So remember the Pentacle, right? That was one type of oxidation. This is another one for that. All right, and then just to finish out this chapter, we're going to talk about an analog of the alcohol. So the functional group now, instead of having O, so remember O is right above S there, right? Group 16. So S can actually be replaced. So instead of OH, it's SH, and that's called a sulfahydryl. And the group is thiol. Okay, that's the functional group. It's still sp3 hybridized, so you have the carbon, right? Tetrahedrocarbon here. Same, similar bond. Remember that the sulfur is bigger, so there's a slight difference in the angle there, but you still get that, bent, a little bit of deviation from the 109.5, so a little bit more deviation because the sulfur is so big, okay, but similar structure there. For naming, you drop the E. Remember, for alcohol, you drop the E and you add OL. Okay, for the thiol, you add that whole name. So drop the E and it becomes thiol. Okay, but often for pronunciation, they leave the E in there. It's easier to say butane thiol than just say butane thiol, like the E being in there.
So on our
You should leave the E. You should leave the E.
Straight. Well,
So
it takes away the E. I want to let you know. It takes away the
if it does,
I'll
okay,
let you know.
you'll let me know.
Butane,
Yes,
yeah.
please. If I'm leading you in the wrong direction on now, please. But usually, because it's a pronunciation issue, but the E usually is there, so you can see these are all from the book, and the book is, the OWL is based on the book, so I'm thinking it will follow that. But if not, if you try one time and you're pretty sure you did it just right, take the E out, just see what it does. If you're having problems, just do it once or twice and then email me, and I can go back and check, and I'll tell you what we were supposed to do. Okay? Of course, the SH is a substituent. Then you name it, if it is a substituent, sulfonyl. Okay, so sulfonyl is the substituent name. So if you have 4 carbons and the SH, right, at carbon 1, so 1-butane thiol. And then mercaptan is the common name, but this has actually been phased out. Iupac no longer, so if you go to a catalog and you look for mercaptans, it doesn't show up. It just says in parentheses C and then the thiol name. So they're actually, Iupac is phasing out mercaptan as a part of the accepted common name. People can still use mercaptan, but Iupac does not recognize it any longer. So we're not seeing it as much, but again, it's just the butyl group, right? 4 carbons, and then the SH becomes that mercaptan name, just like alcohol for the hydroxyl group. So this has a substituent, so 2-methyl, right? 1-propane thiol. But what if there's 2 functional groups? The hydroxyl has higher priority, so you name it as ethanol, right? 2 carbons. But then you have to name the SH as a substituent, so that's when you use the sulfonyl. Does that make sense? So this would be, right, ethanol, but there's a sulfonyl at carbon 2, right? 1, 2, sulfonyl, and then ethanol. So that's for the thiol. As for physical properties, hydrogen bonding is not seen with sulfur, so even though in biology, I know Dr. Galanka, when she teaches, she does use sulfur as a group that can hydrogen bond, and in biology, that's true. So in biological systems, in different solvents and pHs associated with biological systems, sulfurs can, but in organic chemistry, as an atom, it is not electronegative enough to be considered with the hydrogen bonding. So that's, I always like to say that because students are like, well, in my biology class. So in biological system, things can do things a little bit different because there's a context to it. Okay, in organic chemistry, we're looking at the numbers, right? In electronegativity, it's only N, O, or F that are strong enough, right? Have a big enough electronegativity to do the hydrogen bonding. So you don't see hydrogen bonding, which means that you don't have that increase in the boiling point like you see with the alcohol. So the boiling point of the thiol, right, is going to be much lower than the alcohol. So these are considered, in size, to be close in size, and you see 35, 78, 98, 117. So it does increase, though, as the chain length increases, which is something we see as a trend for alkanes anyways. Okay? And then for constitutional isomers, remember that the ether is a constitutional isomer of the alcohol, and there's a huge difference in boiling points. Okay, here you don't see any change because again, there's no hydrogen bonding really here. So you're not losing anything when you make the sulfide. okay, which is the ether, right? There's no more H there. Okay. So a couple of other physical properties associated with thiols. Smell. They stink. So if you've ever been sprayed by a skunk or been in the area where a skunk may have sprayed, it stinks. Okay? And the reason is because there is a thiol associated with that spray. Okay? The natural gas that we use in the lab, you know, natural gas is odorless and colorless, so it actually, we don't even know it's there, but that's the problem. So they put in a little bit of thiol in there so that we can smell it. So that stink is not the natural gas. Okay? It's the thiol that's added to the natural gas so we can detect a leak. Okay? Rotted eggs, also sulfur forms when eggs rot. That's why it smells so bad. Does that make sense? So a lot of things that smell have thiols, and so they can use, and they're called odorants. So does it seem like that would be right? Odorant? It's nasty smelling. Acidity, so for chemical properties, these are more acidic than alcohols because of the size. The sulfur is bigger. You can disperse that negative charge better than you can with the oxygen. So you do see an increased acidity between, right, alcohol. The alcohol here, right, the hydride that's, or hydroxide that's formed. So you can see the pKa 15.7 with the sulfur, it's going to be 7. So remember, as the pKa decreases, the stronger the acid. And so acid-base reactions now, right, are more abundant with the thiols than with the alcohol. So you can see here just an example with the sodium hydroxide. So oxidation is also a reaction that happens often with sulfur in the body especially. So I don't know if you've studied amino acids already in some of your classes, but cysteine has a sulfur, right, a thiol group, SH. And if there's another cysteine in the protein, they can oxidize, right, and form a disulfide bond. And that's really important in protein structures. It holds, right, that structure, the tertiary structure, secondary and tertiary, actually, structures of proteins. So that's basically taking 2 of the thiols, right, and making the disulfide. You can also oxidize to the sulfonic acids. So there are different oxidizing agents that can do that as well.